Orthogonal matrices. Over the next two lessons we examine two important classes of matrices which frequently arise in application: orthogonal matrices and projection matrices. In this lesson, we focus on orthogonal matrices. An orthogonal matrix Q is any matrix which does not change the length of any vector. It may rotate or reflect a vector, but it cannot stretch or shrink it. Let's use this definition to find some other properties of the orthogonal matrix. If the length of a vector v is not changed, then the length of the new vector qv equals the length of the original vector v for any vector v. We square both sides to make computation a little smoother. Recall that the square of the length of a vector is the inner product of the vector with itself. Then we have that qv transpose times qv equals v transpose times v. The transpose of a product is the product of the transposes taken in reverse order. So v transpose q transpose times qv equals v transpose v. Since this statement is true for any vector v, q transpose q must equal the identity matrix. Let's think about what this statement means. This is an important property of orthogonal matrices. In fact, an alternative definition: the inner product of any two column vectors of Q is either 0 or 1. So, the column vectors are all mutually orthogonal. Furthermore, the length of any column vector is 1. We say that the column vectors are orthonormal. This identity also says that the inverse of an orthogonal matrix is equal to its transpose. On a practical note, this makes computing the inverse extremely easy. This is a good point to include a note about orthogonal subspaces. We said that two vectors are said to be orthogonal if their inner product is 0. Geometrically, this says that either one of the vectors has 0 length, or the vectors are perpendicular. We say that two matrices A and B are orthogonal if their inner product is a 0 matrix. This means that every column of A is orthogonal to every column of B. This line is orthogonal to this plane, but two planes in R3 can never be orthogonal, because every vector in one plane is not orthogonal to every vector in the other plane. Another property of orthogonal matrices is that they preserve the angles between any two vectors. Let's see why. Recall that the cosine of the angle theta between two vectors v and w is given by the inner product of v and w normalized by the lengths of v and w. Likewise, the cosine of the angle phi, between the transformed vectors qv and qw, is given by the inner product of qv and qw, normalized by the lengths of qv and qw. The angles theta and phi are the same if the ratios on the right-hand side are the same. We start with the cosine of phi. Because an orthogonal matrix preserves the length of a vector, the denominator is simply the product of lengths of the original vectors. We distribute the transpose in the numerator, remembering to reverse the order of the two terms. Q transpose Q is simply the identity matrix. So, we have that cosine phi is the inner product of v and w, divided by the lengths of v and w, which is simply the cosine of the angle between the original vectors v and w. We'll finish the lesson with a summary of the properties of orthogonal matrices. Orthogonal matrices preserve the lengths of vectors, and they maintain the angles between vectors. This means that they don't change volumes of objects. Q transpose Q equals the identity matrix, which means that SQ inverse is simply Q transpose, and all the columns are orthonormal. Similarly, all the rows are orthonormal. So, orthogonal matrices are really rotation matrices or reflection matrices or some combination of the two. In the next few lessons, we will look at some additional properties. Namely, that eigenvectors of symmetric matrices form an orthogonal matrix.